Okay, last class we just finished page 43, getting us started with all these different methods. Now we're going to try the 5 different strategies on 2 different quadratics and see which ones we're leaning towards, which ones seem more efficient for us, etc. So I'm actually going to do the bottom one first, and then we're going to go up to the top one. Because the top one has a coefficient greater than 1. So looking at this one, I'm going to start with the bottom 3 strategies and then talk about Carlos and Zach's last. So Clarita, remember, is the factor, and Tia's is completing the square, and Tehani's is the full formula. And so let's start with Clarita's factoring. What times what makes -8, and subtracts to give us 4. So all of my options for 8 are 1 times 8. Okay, that doesn't subtract to give me 4. 2 times 4, that does not subtract to give me. In fact, is this actually factorable? What do you think? Are there any other options for 8? No. There are no options for factors for Clarita's method this time. Interesting. Okay. Let's move on to Tia's strategy and see if we can complete the square with this one. So we're going to start by moving the 0 onto the left so that we can bump this over for making space. We go off to the side to do the b work wherever you can squeeze it. B over 2 is going to be 4 over 2, or 2 squared, which is just 4. We're going to be adding 4 and subtracting 4 to balance. How'd you do? Okay, well, next we go and get the perfect square factors for that trinomial, that perfect square that we just made. And at the back, we get -8 minus 4 is just 12, -12. And what'd you get for here inside the parentheses? You got it, the x plus 2 squared factors. So here I am in vertex form, but I'm trying to use this method to solve, so I'm going to keep going by adding 12 to this side. And then square rooting both sides. So I'm going to get plus or minus root 12 is equal to x plus 2. I'm going to subtract 2 from both sides. I'm going to get -2 plus or minus square root of 12 is equal to x. Now to write my final answer, I'm going to flip it around and write -2 plus or minus, but for the root 12, I'm going to simplify that. Square root of 12 is 3 times 4, which is 3 times 2 times 2. So take a minute to think what can come out and what can stay in. You got it. The 2 can come out, the 3 can stay in. There's my final answer. Now, if I get an answer like this with a radical, it means it was not factorable. There was no whole number answer that I could have gotten. So I got 2 real roots, but they're not whole numbers, and that's why it was not factorable. Clarita's strategy wouldn't work in this case. All right, now that I know the answer with completing the square, I'm going to go do the same exact problem with the formula, and if I end up with the same answer, I know I've got it. So step 1, get A, B, C. A is 1, B is 4, C is -8. And then we're going to plug into the formula. The front is going to become a -4. I can tell that -4 over 2 is going to be able to reduce, so I'm going to start to split it up like this now. 2 times 1 is just 2 on the denominators. Notice that the denominator goes with both the front and the back when we're simplifying. And then inside there at the discriminant, 4 squared makes 16, minus 4 times 1 times 8. 4 times 8 makes 32. All right, 16 plus 32 makes 48. So let's go off to the side and simplify root 48. What times what makes 48? Maybe you're thinking 12 and 4. Maybe you're thinking 2 and 24. Either way, keep breaking it down. 12 is 4 times 3. Now, do you see how I already have a pair that can come out? If you wanted to stop here, you could already take out a 4 and leave a 3 underneath. But if you felt the need to keep going, 2 times 2, you'd take a 2 out, take another 2 out, and your final simplified radical is 4 root 3. So we get x equals negative 2 plus or minus 4 root 3 over 2. This is this root 48 simplified to 4 root 3 right there. Now, do you see how 2 goes into 4 2 times? So final answer, negative 2 plus or minus 2 root 3. Look at the answer I just got a second ago, how they match. One was using the formula, one was using complete the square. How'd you do? All right, let's go up and talk about graphing and making a table for this function. If I know that if I stand at the negative 2 and I go 2 root 3 in one direction and 2 root 3 in the other direction, that would be my parabola on a graph. So picture Zach's strategy. Picture that I'm standing at negative 2. That's the middle of my graph, my line of symmetry. And if I go 2 root 3 in the direction to the right and 2 root 3 in the direction 2 root 3, or negative 2 root 3 in both directions, then that's going to give me my two roots. Negative 2 plus 2 root 3 and negative 2 minus 2 root 3. Now I don't know exactly where 2 root 3 is. I know root 4 is 2. 2 times 2 is 4. So I could go 4 in the right direction. I could go a little bit less than 4. And in the left direction, I could go a little bit less than 4. So that just kind of gives me like a common sense estimate of it. But either way, we know it's going to be somewhat in the right direction, the same distance in the left direction from that line of symmetry down straight of the negative 2. So Zach's strategy of graphing this, what would be his two options? Since it's not factorable, graphing from factoring won't work this time. So he would have to put this into vertex form. Well, we just got that down here using Tia's strategy. Here's vertex form. So I can see that the vertex is actually at negative 2, negative 12. So negative 2, 2, 4, 6, 8, 10, 12, negative 12. There's Zach's strategy using the vertex from Tia's strategy, using the roots from Tia's or Tehani's strategy. We could get this on the graph. The other way we could get Zach's graph is just by straight up doing Carlos's table. The trick for Carlos's table method is picking smart x values. For example, if I just picked negative 2, negative 1, 0, 1, 2, I would only get part of a parabola because we know that the vertex goes through negative 2. So by doing a little bit of work and figuring out where my vertex is first, you can purposefully pick negative 2 as the middle, pick some points on the left of the vertex and some points on the right of the vertex to make sure you have a nice symmetry. So choosing smart x values is necessary when doing Carlos's strategy. So here I go, plugging in negative 2, the vertex first. Well, we just did this below, and we already know what the vertex is. So negative 2 squared is 4. 4 minus 8 is negative 4. Negative 4 minus 8 is negative 12. Hey, that's what I already knew my vertex was from Tia's method. So negative 2, negative 12 is that vertex point of my parabola. Now when I plug in negative 1 and negative 3, these are going to yield the same output. And when I plug in 0 and negative 4, they're going to yield the same output. So if I just plug in 1, I can fill it in for both values. And if I plug it in for the other one, for both values. So plug it in negative 1 squared plus 4 times negative 1. Negative 1 times negative 1 is positive 1 minus 4 is negative 3. This is going to give us negative 11. Plug it in 0 squared plus 4 times 0 minus 8. We know it's always just that c value, that constant at the end. I know that this is also going to be a negative 11, and I know that this is also going to be a negative 8. So we would go put those other dots on the graph right here at negative 1, negative 11, and 0, negative 8. All right, now we just have a couple more points on the graph because of Carlos's strategy. So all these methods work, but which one are you leaning towards? And notice how we sort of rely on each of the other methods to help us with our current method. All right, now I'm going back up to this top one, our last one today, where now it has a coefficient in front greater than 2. Just because it has that does not mean we can't factor it. In fact, this one is factorable. It just requires the x and the t method because there's a 2 in front. Oh yeah, remember that? So what goes in the top is not just a 1, but 2 times 1, or 2. And in the bottom is 3. What times what makes 2? So my two factors are a positive 1 and a positive 2. So the factor 2x plus 1, that one's already done because it can't be simplified. But the factor 2x plus 2, see how a 2 can divide into both? So this factor reduces down to x plus 1. If you do not remember the x and t factoring method, there's also another method called guess and check, where you just come up with two possible factors by saying what times what equals 2x squared. It's got to be a 2x and x. What times what equals 1 at the back? Well, it's a prime number and it's only 1 times 1. So in this case, using guess and check would be super simple because it would give you these two factors right off the bat. Finally, besides the x and the t, besides guess and check, we know a third way that we could work through this, and that was the box method, where you said what times what equals 2x squared and 1. So you'd have to put the 2x times x on the outside, and you'd have to put the 1 times the 1 on the outside, and then test it. And it totally works out to my trinomial. Either way, these are our factors, 2x plus 1 times x plus 1, and now we solve. So I'm getting negative 1/2 and negative 1 are my two real roots. Okay, let's go try completing the square method on this. Remember that we're going to move the 0 to the left on this one so that we can make space. But notice there's a coefficient greater than 2, so we're already like, oh man, this one's going to be one of those ones where I have to divide out a 2. So I divide out the 2, and right here is where I'm like, oh no. 3/2 x. So I'm dividing by 2 just to make a 1 square that I can complete, and I already have a fractional b. Not cool. So when I go off to the side to do the b work, I go 3/2 divided by 2. That's going to be 3/2 times 1/2. Do you remember keep, change, flip? Or 3/4. 3/4 squared is 9/16. I'm going to be adding 9/16 and subtracting 9/16 to balance. Don't forget the times 2 because of this. This makes the x plus 3/4 perfect. And then plus 1, I'm going to change this into eighths. So that's 8/8 is another way of saying 1. And the reason I did that is because negative 9/16 times 2, that would turn into negative 18/16, and 2 can divide into negative 9/8. So all that work gives me negative 9/8. And so my final answer at the very end, at the back there, I mean, is negative 1/8. I now add 1/8 to both sides, and I get 2x plus 3/4 squared. I then have to divide by 2 to both sides because I'm trying to isolate this perfect square. So I'm going to start pulling my work up here in just a second. So 1/8 divided by 2. Again, keep, change, flip. It's going to become 1/16. So I'm going to get 1/16 is equal to x plus 3/4 squared. Are you starting to think what I'm thinking? I would not choose Tia's strategy on this one, right? So I'm going to square root both sides. I'm going to get plus or minus 1/4. The square root of 1/16 is 1/4. I'm actually going to put that on the right-hand side. Hang on. And then on the left, I'm going to get x plus 3/4 when I square root x plus 3/4 squared. When I minus 3/4 to both sides, my final answer is negative 3/4 plus or minus 1/4. So I get negative 3/4 plus 1/4. That's negative 2/4 or negative 1/2. And then I get negative 3/4 minus 1/4. That's negative 4/4 or negative 1. I get my two answers of 1/2 and 1, just like I did right here. But man, was that gnarly. You have to be super good at fractions to do Tia's strategy of completing the square on that one. Yes, it is possible, but did I like it? Not really. Let's go try Tehani's and see what you guys think for that one. Sorry, guys. All right. For Tehani's, we get A, B, and C. We say x equals negative 3 plus or minus square root 3 squared minus 4ac all over 2a. So that gives us negative 3/4 in the front, 9 minus 8. Nine minus 8 is the square root of 1, which really just gives us negative 3/4 plus or minus 1/4. Hey, that's what I just got down here with Tia's terrible method. And so we know that our two real roots are going to come out to negative 1/2 again from our work down there, and negative 1 from our work down there. And so I think that the formula went way faster this time than Tia's method, right? But what was my preferred method of all of this? For sure, the factoring. What do you guys think? Okay, finally finishing off with Carlos's strategy. Carlos would make a table of values. We now know that this is going to be going through a line of symmetry of -3/4. And so when you're choosing a table of values for Carlos's, choosing smart X values, if I choose -3/4 and then pick one value on one side and values on the other side, that will give us our symmetry. Plugging in -3/4, in for x squared, we could do a lot of work there to get that value. Do I prefer this table method with fractions like that? Definitely not, right? Like, I'm still leaning towards this being the preferred method. And then Zach's strategy of graphing, I know the line of symmetry, like if this is at 1, or let's make that a half, and this is, so -1/2, -1. I know my line of symmetry is going to go through -3/4. And I know that my two roots are going to be +1/4 in this direction and +1/4 in the other direction. And so I'm going to have some sort of a parabola like this for his graph. So again, relying on the other strategies to help make Zach's strategy, or just if you don't want to deal with plugging in a fraction here, you can deal with the whole numbers, but you still need that vertex eventually. It turns out that from our vertex form right here, we can see that our vertex is actually -3/4, -1/8. So this down here is -3/4, -1/8. So like this way down here is at a -1/8. And we can also see that the stretch is 2, so it's going up 2 times as fast as the parent. So as you can see, the more quadratics we practice with, the more complex these different options can be. But the goal is for you to select the most efficient method. And I believe you can do it. Please turn in a picture of this page, page 44, into this bin, please.